This resource is the third in a three-part series on solving triangles, or finding missing information for a triangle given some combination of side lengths and angle measures for any triangle. Part 1 considers the law of sines. We define the law and provide the situations to which the law best applies. We look at an example of each case. Part 2 considers the ambiguous case, where the provided information allows one solution, two distinct solutions, or no solutions. We consider examples demonstrating each case. Part 3 considers the law of cosines. We define the law and suggest its best use. We look at examples for each case. In another resource series, we defined the trigonometric ratios, sine, cosine, tangent, secant, cosecant, and cotangent, as methods to relate the lengths of the sides of a triangle and the measures of the angles of the triangle. However, those ratios required the triangle be a right triangle. One method to relate the sides and angles of any triangle is the law of cosines. This law works like an extended Pythagorean theorem that works for any side of any triangle. It states that the square of the length of a side equals the sum of the squares of the lengths of the other two sides minus 2 times the product of the other two lengths and the cosine of the angle opposite the side we are looking for. This formula can also be manipulated to have the cosine of the angle solved for instead of the square of the missing length. Each of these versions of the law of cosines are used in solving triangles where we are given specific patterns of information. The first pattern of given information for which we use the law of cosines is if we know the lengths of two sides and the angle in between those two sides, or side, angle, side. It is important to distinguish this from the ambiguous case, where the known angle was not between the two sides. The side-angle-side setup will only have one triangle possible. To solve triangles with this pattern of given information, first find the missing length of the final side. We will want to use the first version of the law of cosines to accomplish this task. Next, we will find the measure of the angle opposite the smallest side using the law of sines. Set up the appropriate ratio, cross-multiply and divide, take the inverse sine of that result. We finish by subtracting the sum of the angle measures we know from 180 to find the size of the last angle. Let's see an example. Suppose we know that angle A is 120 degrees, length little b is 8, and length little c is 7. We know the lengths of two sides and the measure of the angle in between them, so we have side, angle, side. We want to use the law of cosines to find the length of side little a. Plugging in our given information, we have a squared equal to 8 squared minus 7 squared minus 2 times the product of 8, 7, and the cosine of 120 degrees. Calculating, we find that a squared equals 169. To find length a, we take the square root. This gives us a equals 13. Now we need to find an angle. To set the tradition, we will find the smallest angle, which is opposite the side with the smallest length. Because we know a length of a side and the measure of the angle opposite it, we can shift to use the law of sines. We set up our proportion, 13 over the sine of 120 degrees, equal to 7 over the sine of angle C. Cross-multiply and divide. This gives us sine of angle C equal to 0.4663. To find angle C, we take the inverse sine of the decimal amount and find angle C has a measure of 27.8 degrees. Now we can find the measure of our last angle. We subtract the sum of the measures we do know from 180 degrees. This tells us angle B measures 32.2 degrees. But what happens if all we know are the lengths of the three sides and have no information about the angle measures? First, we want to find the measure of the largest angle. We will use the second version of the law of cosines, which is solve for the cosine of the angle to find this angle measure. Then we use the law of sines to find the measure of the smallest angle. We finish solving the triangle by subtracting the sum of the angle measures we just found from 180 degrees to find the remaining angle measure. Let's see an example. Suppose we know that the lengths A, B, and C are 10, 8, and 5, respectively. We need to find the measures of the angles to solve this triangle. First, we will find the measure of angle A, which is opposite the longest side. To do so, we use the second version of the law of cosines. This gives us the cosine of angle A equal to the quantity 8 squared plus 5 squared minus 10 squared, all divided by 2 times 8 times 5. Calculating, we find the cosine of angle A equals negative 0.1375. To find the actual measure of angle A, we take the inverse cosine of that decimal amount. We find that angle A measures 97.9 degrees. Now we can use the law of sines to find the measure of the angle opposite the smallest side. We set up our ratio so that we can ultimately find the measure of angle C, which is opposite the smallest side. Cross multiply and divide. We find that the sine of angle C equals 0.4953. We take the inverse sine of the decimal amount to find angle C measures 29.7 degrees. Now we can find our remaining angle measure. Subtract the sum of the angles we know from 180. Our final angle measures 52.4 degrees. We use the law of cosines to solve triangles where we know more information about the lengths of sides than we do about the measures of the angles. This law takes two formats, depending whether we want to use it to solve for a missing length or for a missing angle measure. Either way, the calculations are more numerous and involved than the law of sines. Once we know a length of a side and the measure of the angle opposite that side, it is much easier to use the law of sines to find a second angle measure. Then subtract the sum of the angle measures we know from 180 degrees to find the final angle measure, and our triangle is solved.